Okay, thank you. Yes, so I will give you some introduction to very fast rotating dead stars. So a neutron star is formed after a supernova explosion. That's an explosion that looks somewhat like that, which is the explosion of a very massive star that's much heavier than our sun. And these stars, when they explode, their cores collapse into forming either black holes, which Victoria will tell you more about, or forming neutron stars. So neutron stars are the leftover of supernova explosions. They are very, very dense stars, or dead stars. They're actually so dense that they're more than 1.5 times as heavy as our sun. And they're only about 20 kilometers in diameter. So they would be about the same size as Manhattan, or you would be able to fit one in between Leiden and The Hague, which is quite interesting considering that it's much, much heavier than our Earth. It's actually so heavy that 1 teaspoon of neutron star material would be about the same weight as one of the pyramids of Giza. But how do they become this heavy? And what's going on inside of them? Well, if you have an atom, you have the nucleus of the atom, which consists of protons and neutrons, and then you have the electrons around it. All of this atom is actually quite big, and it takes up quite a lot of space. So much so that in normal material, if you have 2 atoms next to each other, it would correspond to having 2 people at 100 kilometers distance of each other. And then when you collapse the star, you squeeze in the atoms together, so you squeeze electrons into the protons of the core of an atom, and you form neutrons, hence the name neutron star. So you have more neutrons than you have in normal material. And that actually corresponds to squeezing 2 people into a really tiny bus, and everyone is very tightly packed. So that's how we end up with so much matter and material and so heavy cores on such a small space. But neutron stars are one thing. So pulsars are actually a type of neutron star that has a very, very large magnetic field, and they rotate really fast. So fast rotating dead stars with a big magnetic field. The most important thing about neutron stars are that their rotation axis and the magnetic field axis is off center, so they don't align. And this is because the radiation that we see, either in radio or in X-ray, and I'll come back to these two, they form at the poles, at the magnetic poles. So when we observe, we have to be in the line of sight, and if the magnetic field line was aligned with the rotation axis, we wouldn't see anything. Either we would just see a constant source of light, radio or X-ray, or we wouldn't see anything at all. So because it's tilted, we can see a pulse or a beam towards us occasionally. And that would look somewhat like this. So when we're in the line of sight, we see a peak or signal. All right. Pulsars were discovered in 1967 by Jocelyn Bell Burnell when she was a PhD student at Cambridge. She was actually looking for active galactic nuclei, but what they saw all of a sudden was sort of small peaks in their data, and they wondered what this was, because no one had observed these systems before. So they took a closer look, and they saw that they saw peaks at specific time intervals, and always at the same time. There was always the same amount of time between the peaks that they saw. And at first they actually didn't know what this was, which also gave the name to this. So their confusion of what it was meant that they also considered if it was aliens. So the first name that the first observed pulsar got was LGM1 for Little Green Men 1. They later found out that it wasn't aliens, it was pulsars, and it was actually the first confirmation that neutron stars and pulsars existed, because before then it was only theorized. Her supervisor, Anthony Hewish, later went on to winning the Nobel Prize for this, along with Martin Ryle. There are different types of pulsars. So I already mentioned that we see it in both X-ray and radio. X-ray pulsars are always in binary systems, where you have a main sequence star that's a star that's similar to our sun. And then you have a compact object, so typically you have a neutron star, and for my purpose you have a neutron star. It could also be a black hole. And I think Victoria will come back to something similar to this. And then at some point in the stellar lifetime, a star expands and it fills out something we call a Rush lobe, which is a border where within that border all the material is still gravitationally bound to the star. If it expands across this border, it can overflow and it can fill up the other part of the Rush lobe, so the Rush lobe is this blue line. And when it overflows into the other star's Rush lobe area, it can create an accretion disk around the neutron star, and it forms a disk because everything is rotating around each other and the pulsar is rotating. So you end up with a disk. And this disk, it's from this disk that a pulsar can accrete material along the magnetic field lines. So what you would see is that these lines that move is material that's picked up from the disk and it ends up on the magnetic poles. And that's actually where X-ray radiation is then formed. It's heat that shines out from the poles. So it's thermal emission. One important thing that the X-ray phase does is that it spins up the pulsar. It carries the material that overflows from the companion star, the main sequence star, carries an angular momentum that can spin up the pulsar. So it's just energy that it carries onto the pulsar. So we can create millisecond pulsars from this. If we look at radio pulsars instead, we have radio pulses in sort of two categories. We have a clump of radio pulses up here and a clump of radio pulses down here. So the y-axis is the change in the spin, in the rotation of the pulsar, and the x-axis and the axis down here is the spin period of the pulsar, so how fast it's actually rotating. Because pulsars do slow down eventually. They can also spin up. So the spin period can change, and that's what we measure here. I should just say that these lines are the age, and the other way we have magnetic field lines, and I will come back to the magnetic field a little bit. We have one class up here that are young pulsars. We see a lot of these young pulsars, they're often isolated systems, so they're not in binaries, which also means that they're quite often spinning slower. So these pulsars have spins of a few seconds, 0.1 to a few seconds. And as an isolated pulsar would just be a neutron star that rotates with a magnetic field. It doesn't have a companion. The radiation itself is radio, and that just means that you have particles that are accelerated in the magnetic field, and that creates the radio beam. If we move on to the faster spinning pulsars, so these were slow and they had high magnetic fields, and we move on to the faster spinning. These have spins of milliseconds. We also observe that these systems are almost always in binaries, which means that they have probably been spun up through an X-ray accreting phase. So we would have the high mass star and then the low mass star here. The high mass star explodes as a supernova, as I started out saying, and we still have the low mass star. This phase will probably be very short because we don't really observe any radio pulses that are slow in binaries. And the main sequence, their companion star, will probably quickly expand and fill the Rush lobe, and we'll form this accretion disk, as I said earlier. And then we end up having, when accretion stops and you've spun up the pulsar, then you will end up having a companion star of some sort that's been ablated and stripped of a lot of material. And you will have a companion, or the primary, that is a millisecond pulsar. So that's how we end up having millisecond pulsars. These millisecond pulsars are quite important, and it's part of why I find that it's really fun at looking at pulsars. Because what we can actually do with pulsars and what we can use them for is as extreme laboratories. So one thing that we can do is that we can look at magnetic fields. Now the magnetic fields of pulsars are somewhere between 10 to the 8 to 10 to the 15 Gauss. And that probably doesn't mean that much to many of you, but if we compare it to the Earth magnetic field, which is very sufficient in protecting us from the solar wind, for instance. The Earth's magnetic field is only about 0.5 Gauss, and the magnetic field of our sun is about 1 Gauss, which is 10 to the 8 times less than what we see the weakest magnetic fields in pulsars have. So at some point when the star collapses, you increase the magnetic field. And this is actually one of the unknowns of this field. But we can test physics and we can try and find out why these stars have such huge magnetic fields by looking at pulsars. Another thing that's interesting about pulsars and neutron stars, just neutron stars in general, is that we have no idea what they consist of. So I said that atoms in the neutron stars really squish together and you have a lot of neutrons instead of sort of protons and neutrons and electrons together. But this creates some funky physics, because we don't know what's going on. We have some sort of outer layer and we will have some sort of crust, and then we have something inside the core of a neutron star that's probably a superfluid or something fluid like that we are not sure what it is. And there's a lot of people that's trying to figure this out. And recently there is a telescope attached to the International Space Station called NICER that's supposed to look at the equation of state of these neutron stars. And terms like spaghetti phase is also used here. So some people theorize that you have like lasagna plate layers, or you can have like clumpy layers that are like gnocchi, or other types of spaghetti. Pick one, it's probably in some theory. What I really love about these systems is that we can also do precision chiming. So we can use pulsars as really precise clocks. And that is what I've been working on for the past 4 years. This is basically what I'm looking at when I'm looking at data and looking at pulsars. So what we do is that we observe each time a pulse hits our telescope. So each time for X-ray we observe photons, for radio we observe just a radio beam. And what we see is the time of arrival of the pulse, and that's what we measure. We measure every time the pulse is in our direction. So essentially, if you imagine that every point is us measuring a pulse, what we then do is that we make a model, and we fit this model to our data. The model includes the spin of the pulsar. If it's in a binary, it includes the orbital parameters of the binary to describe exactly what's going on in the system. And when we do that, we try to take into account every possible variation to the system that we can find. And when we're successful with that, we find residuals which are flat. So residuals are the difference between our model and our data. And we can have this model fit to our data so exact that we can do it down to an error of a few hundred nanoseconds in time precision, which is quite extraordinary in astronomy, because usually you have quite high errors when you're looking at things very far into space. People are like, within a couple 100,000 kilometers, it's fine. But we can do things down to a precision of nanoseconds. This example is down to 0.5 milliseconds, which is also quite precise still. If we're not entirely good at fitting our model, we would find structures in the residuals. So we could find an orbital period that's off, then we get a similar signal as this in our residuals instead of flat residuals. If we have the position of the pulsar that's off, then we also have some sort of sinusoidal evolution. And all of these different parameters that we're using in a model gives different signals in the residuals if we're not fitting them completely correctly. Which is where it gets fun. Because one of the things that we can see if we're looking at residuals is if there are other bodies orbiting this pulsar. And that's actually how they found the first exoplanets. So this is back in the mid-90s, that people saw that there was some sort of sinusoidal signal in the residuals, and they had no idea what it was, because it wasn't the binary companion or any other thing. And the only thing that it fitted with was if there was a planet around this pulsar. That was the first exoplanet. Another fun thing that we can use it for is apparently to find ourselves. So this is the plate that was sent up with Voyager 1, which has now exceeded the solar system limit. And if we look at this part of the plate, we see 14 spikes out, and that's actually coordinates for 14 pulsars that if aliens can read the coordinates, they're apparently given in binary numbers on this, then they can find the coordinates for the 14 pulsars, and by sort of crossing all of these lines, they can find our sun, and thus find us. Because I'm sure aliens can read binary numbers and know exactly where the pulsars are. Another really cool thing is that we can actually use pulsars to find gravitational waves, or at least we think so. So you've probably all heard that gravitational waves exist and have been found, I would assume. There's been a lot of press going on about it the last couple of years. First time it was detected was in 2015, in August 2015, I think. And gravitational waves are waves that stretch the fabric of time and space. It's like you could see that the Earth is moving, so everything would be stretched and compressed. Of course, not in this scale, so it's exaggerated a lot. A lot. But it would correspond to throwing a rock into water and you see the ripples. And that's actually what happens. So we see waves coming through space. On Earth, people have detected gravitational waves using LIGO, which is 2 American telescopes. So one is I'm guessing this one is the one in Louisiana, I think, and this one is in Washington State. There's now another detector in Italy called Virgo, and these are collaborating to find gravitational waves. The ones that they've observed have originated from black holes colliding or from neutron stars colliding. What we would be able to see with pulsars are supermassive black holes, or perhaps a signal from around the time of the Big Bang, so from very old universe. And the way that we would be able to see it is from signals in the residuals, but we need a lot of pulsars to do this. So we need a lot of pulsars that are strategically placed on the sky and spread out over the entire sky. And then if you see some sort of signal going through it, you will see that the signal we see from the pulsar is slightly off and it varies a little bit. And when we see that in all of the pulsars, we get a collected signal that can show us a gravitational wave. At least that's the idea. And I've slowly been moving my way into working on this. And I've been working on some systems that are usually not stable pulsars, but we do see some sort of systems that are stable pulsars and can be used in pulsar timing arrays. And for doing this, we need very precise pulses, so that's when we need timing to a few hundred nanoseconds, preferably less than 100 nanoseconds precision. So all in all, we can use pulsars as extreme laboratories to look at magnetic fields or the interior of the pulse of a neutron star or gravitational waves. We can also look at other fun things like plasma and how accretion works. So they're incredibly extreme and good laboratories to use for things that we just cannot observe on Earth. Thank you.